I'm going to present more on modems. Intro to synchronization. Synchronization is a topic that is frequently excluded from a lot of comm theory. It is one of my favorite things to play around with. Oh. Mute there. Yeah. Okay.
Yeah, go ahead. I muted her.
Thank you. It's very distracting. Everyone knows of a modem as modulator, demodulator, but it's really a lot more than that now. This is my definition. A modem is a system that allows reliable transmission of information over a channel. So this definition has a lot of stuff packed into it. So some of it we're going to talk about, some of it we're not. Specifically, we won't talk too much about what information is, but we will talk a little bit about channels. Modems are in just about everything now that communicates in any way between machines. They're so ubiquitous that we take them for granted. It used to be like a box that you stuck on your phone, but now they're just in everything. A couple of extreme examples of some modems is the good old telegraph sounder at 45 bits per second. It's been around forever and ever. You may not think of it as a modem, but the channel is the wire. And the modulation and demodulation is done by the operator using the nonlinear magnetic element to sound it. On the other end is this 100 gigabits per second fiber channel modem, where hundreds and hundreds of these are arrayed in data centers. So they're kind of doing the same job, just there's a heck of a lot of these little guys in this big guy. In fact, this is actually about the same size. To me, modems are really, really interesting because they take all of comm theory and a lot of circuit theory and a lot of things about radios, and they smash it all into one fabulously complicated thing. I showed you guys a video last month that was 8 minutes long about my master's project that I did and had all these charts. So that video was super fast, and there was really no explanation of these things. So I structured this presentation around trying to understand these charts. And these charts are the information flowing through the receive side modem all the way from where it's first detected to where the data is recovered and output into the machine or computer. So hopefully after I do this presentation, these won't be such a mystery. And if you want to learn more, you'll have some tools to do so. Where I'd like to start, yeah?
Can you go into like production mode just to give us a little bit bigger a display?
I can try. This thing doesn't ever want me to share the right screen, but let me see if I can do it.
Well, you can go to slideshow, set up slideshow.
Yeah, I know.
And then change that.
It's just what your thing thinks my monitors are and what I think my monitors are different. So I'll share.
Swap them in PowerPoint.
One. Oh, I know you can do everything. The question is, can I do it right at this exact moment?
So if you go to slideshow, click set up slideshow, and slideshow monitor, change it from automatic to primary or 1 or 2, whatever you want.
Okay. It's not what I did, but it's equivalent. Okay, now let me figure out how to change slides on this monitor. Okay, how's that? Better? Thumbs up. Okay, so each one of these slides has so much stuff in it. So if it doesn't make sense, I think that's okay. What I'm trying to accomplish is a whole bunch of different crumbs and stick some links in there. So most of the slides have a link here, and you have this electronically, so you can go to these links and read more about all these stuff. And the links are mostly probably the most pertinent or most important point, or at least that I thought of. And that usually comes with these charts. So the signal noise ratio is something that we all have a pretty good idea of what it is because we're amateur radio operators. But there's a lot of very technical specifics to how signal noise ratio is used and expressed specifically in communication systems, and very much so in modems. one thing that's not commonly done is to normalize the signal noise ratio to 1 hertz. And you see this N0, this is a 1 hertz noise bandwidth. What this allows us to do is compare different systems that have different bandwidths. So mostly we're used to comparing radios that have sort of similar bandwidths, but you can be very confused easily by that. And one thing that happens a lot is when people look at like WSJT and they say, well, what is the reference bandwidth? Well, using a reference bandwidth is kind of silly. You just reference it to 1 hertz, N0, and then everybody's using the same no matter what. And that's what this N0 is. So now we can think of our signal in 1 hertz bandwidth relative to this noise in 1 hertz bandwidth. So everybody's normalized. The next thing we want to do is we want to think about, okay, well, the different kinds of signal may need different amounts of energy to communicate some information. And the smallest unit of information is a bit. Is it present or not? So really what you're interested in is the energy to transmit 1 bit versus the noise in 1 hertz bandwidth. So this is just boiled down EB, energy per bit, to the noise in 1 hertz bandwidth, the noise energy. This noise is referred to as AWGN, additive white Gaussian noise. Basically what it means is this frequency spectrum is flat, and the probability distribution, which is kind of a fancy word, but it's just what is the probability of a particular value around a mean occurring. So this equation is the Gaussian norm. And what's interesting about this is that it's a square in the exponent, which means it's symmetric about the origin, which is the mean value, and the spread is proportional to this sigma. So this is just an exponential function that's symmetric around the origin, and it's characterized by 2 variables, the mean and the standard deviation. The actual random value, the thing that's changing, is this x. So when you say noise expressed as this f of x, the x is the random variable. The random variable is a fairly complex concept, but in terms of noise, it's just if you have a trial where you pick a value, it's one of these values, and the probability of that value is this. So using this expression, and we know if we can figure out how much energy per bit, reference it to 1 hertz bandwidth, we can compare everybody to everybody else. And then if you want to unnormalize that to your radio, then you can go backwards using this ratio, the information rate, the channel bandwidth, and you get the carrier noise ratio, which is the usual SNR that we would talk about. So this may seem like blah, 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 but this understanding what the energy per bit relative to the noise in 1 hertz bandwidth in a flat white noise channel is really central to all these things. So although we won't detail this too much in the presentation, I'm just going to assume that, okay, you know what this means. And you can look it up later to understand this more. Let's see, change, here we go. Okay, the next thing that surrounds signal noise ratio is bit error rate, and that is if you send a certain number of bits, in this case here again, we're going to normalize. If we send 1 bit, what's the probability of error? So these bit error rate curves are the x-axis is the independent variable is the energy per bit to the noise in 1 hertz bandwidth in decibels. So it's just a ratio. And if you sent 1 bit, what's the probability of that bit being an error? And these are decades. So here it would be 10%, and then 1/100th, and so forth. So what these charts show us is that for a particular amount of energy in a bit ratio to the noise power, it tells us what the performance of a particular modulation or coding scheme or a combination of both is relative to another one. So these are all normalized to this 1 hertz bandwidth and the 1 bit error rate, so that I can say, well, what is better, BPSK, which is biphase shift keying, or FSK, coherent or non-coherent. Might not know what these different things are now. It doesn't so much matter. Is to understand what you're looking at. What it is as I increase the energy available, so more energy is a higher ratio, then the probability error will drop, which is what you expect. At a higher signal noise ratio, you have less errors. And you can compare the rate that each one of these reduces with increasing signal noise ratio. So when you design a system, you can say, well, I can only achieve 10 dB, and I want an error rate of 10 to the minus 4. So you say, okay, well, I know that FSK isn't going to work. I have to use differential phase shift keying or binary phase shift keying. This helps you compare these systems. One thing that you'll notice is all these things, this one, this one, this one, are coherent, which we'll talk about what that is. They're better in terms of their error performance at a particular energy, but it comes with some burden. That burden is primarily synchronization, which is what we want to talk about. Another thing that is confusing with bit error rate charts is symbol error versus bit error. We'll address what a symbol is, but a symbol is a modulation state, and it can represent more than one bit. So from a very simple standpoint, if you have a state that has n bits, the symbol error rate is just a relationship of n. It turns out that's only approximately true because you can change around how the symbols are mapped, which we'll touch on a little bit. You can control the probability in a constellation. Let's say if you have an infrequent letter, you put that in an infrequent position, so that it won't be quite this. But for most cases, for the purpose of understanding, you can just say the relationship between the symbol error rate and the bit error rate is just the number of bits per symbol. And this link will explain it much better. Oops, here we go. So we did say the word channel, which most radio operators kind of know what a channel is. But a channel encompasses a lot of stuff. It's much more than just so many hertz wide at a particular frequency. It's any medium. So it could be a wire, it could be a fiber optic, it could be an underwater path, it can be a radio path, it could be a microwave path in outer space, it could be an indoor path. And there's a lot of characteristics of those channels which will help us determine what modulation we need, and then the modulation we choose will determine what kind of synchronization we need. So any medium that provides us a channel has finite delay. It's typically modeled with white Gaussian noise. This isn't always true, depending on the hardware, but it's a good approximation. And it has, go ahead, someone had a question? No? Okay, it could contain impairments. This is the most important thing for the channel, multipath. We don't deal too much with multipath at HF, but at higher frequencies, you can start seeing where this is a problem. So in narrowband channels and long wavelengths, multipath doesn't have too much of an issue. But as you go higher in frequency and you have more bandwidth, multipath becomes a problem because it functions like a filter, and it may not only causes fading, but it also causes frequency-dependent fading, which is terrible. It definitely has to be repaired. Doppler, which we see in satellites, Doppler just means that the frequency is changing at some rate. It could be linear, it could be nonlinear, depends on the trajectory of the receiver and transmitter. But later we'll see that frequency, knowing the exact frequency is very important, and Doppler fouls it up, so that's part of the channel. Interference, that's an obvious one, we all have to deal with that. Interference is often multiple users in the same band. Like Wi-Fi, there's not too much environmental interference, but there's a lot of interference from other users. So all that gets binned together. Distortion and dispersion. Distortion can be described as a lot of different things. In a wireless channel, it's fairly linear. So you don't have to worry about nonlinear amplitude distortion, but in fiber or in underwater, you definitely do. And other types of non-radiative medium. Dispersion can happen in a wireless channel, and it's primarily due to multipath at low frequency, but absorption lines and other kinds of atomic effects can cause this. Dispersion is just change in phase with frequency is nonlinear. So it distorts the group velocity, so the different frequencies travel at different speeds. When hardware is included in a channel, which may be, depending on the model, frequency and phase error just from the hardware. Timing error is always a problem. even a GPS synchronized clock has some error relative to some other clock. Distortion is a big problem because electronics brings in nonlinear distortion, so spurious, out-of-band emissions, unintentional emissions, compression, third and fifth order. These are all things that we won't talk about, but they exist. And then non-Gaussian noise, which is colored noise or phase noise, 1 over F noise. All those things are synonymous. So this is a statistical phenomenon that's often not addressed in things that you'll find online. So all this stuff can be lumped together into a transfer function. If it's a wireless channel, it can be a linear transfer function, which is very handy for computation. Oh, I just said that. So times when you don't have a linear channel is when you're trying to communicate through plasma. Like if you put a signal through the ionosphere, you might have nonlinear behavior. And also very commonly under fiber optics under high power. So for very long haul stuff where they're turning the power way up, there's a number of phenomena that cause nonlinear behavior that would not be captured in a simple transfer function because there would be an additional term here which would be amplitude. So this is frequency, time delay, and time variation. One thing to note is the channels that we deal with, because mostly our wavelengths are long, except for microwave operators, but the channels are very narrow band. So these are all mild channels. There's hardly any channel effects that need to be corrected, so it's not very intuitive. Human listening to the radio can tolerate a very, very small amount of impairment, not too much. And anytime we have QSB or detuned single sideband or something like that, that's still very mild. So the point here is that a modern modem on like a Wi-Fi channel can correct very, very bad channel conditions and still achieve low error rates. So I guess the big question is, well, how much data can you put through a channel? This is a very famous theorem that maybe a lot of you know about. It's the absolute lower limit using a thing called the information matrix. So we're not talking about what information is and how to manipulate it, but this is something to look up because there's a lot of really interesting things surrounding what is information, what is this information matrix. The proof is really hard, so I'm not going to even try it. But what Shannon's channel capacity says, which is really amazing, is that for an arbitrarily low error rate, a particular amount of bandwidth has an absolute minimum capacity. So all it says is, if you know the bandwidth and have some error rate, which can be made arbitrarily low, you know exactly how much data you can put through it. There's no one can say, oh, I can make a better radio, or, oh, this is a little bit better. You know the absolute limit of how much information you can put in a particular channel. What's really awesome about that from an engineering standpoint is no matter what anybody thinks, the channel capacity is the absolute maximum that you can achieve. So there's no reason to try to do better than that. People have got within fractions of a dB of it, but not quite all the way there. Like OFDM using turbo codes can get pretty darn close. So that's another complex topic. One thing I'll make a point of repeatedly throughout this presentation is all those relationships or things you'll read about achieving so many dB within channel capacity, they all include the assumption that you're already synchronized, but they never say that. Okay, so just an example, I took a CW channel. Let's say we have a 250 hertz filter, and we have a really, really weak signal, just about a few dB out of the noise. If you use the Shannon channel capacity theorem, we can stuff 457 bits per second in there. So 50 words per minute is 41 bits per second. So 50 words per minute is pretty fast, but we can do 10 times better than that. You can send 549 words per minute in a 250 hertz filter, 250 hertz channel. Now you can't do that with on-off keying. You couldn't do it with CW, but this is what's possible. So that's pretty amazing, I think, is that you can put 550 words per minute in this skinny little channel. So how the heck do you do that? Another thing that's not obvious, but you can see it in the channel theorem, is that it's dependent on the bandwidth and the signal noise ratio. Like normally, if there's one person in a channel, if they have a louder signal, we wouldn't think that we could put more data through it. But that is absolutely true. The higher the SNR, the more data you can put through. And this is a really important concept that relates back to these curves. So for a fixed amount of energy, a larger signal noise ratio gets you lower error rate, which corresponds with being able to put more information in the channel. So if we just think about what is possible with on-off keying, knowing that the Shannon capacity is 549 words per minute, we also have to obey the Nyquist criterion. So if we just use on-off keying and we look to the first null, so using the two-sided bandwidth, we could do 150 words per minute. So clearly the channel capacity is way more than 150 words per minute. It's 549 words per minute. So we have to do something else. Commonly people think, oh, we just use coding to get from here to here, but that's not actually the case. Although coding is crucially important, also using more degrees of freedom or putting more bits per symbol in your modulation scheme is really, really the key. Coding plus degrees of freedom gets you from 150 words per minute to 549 words per minute. So I guess probably nobody could ever copy 549 words per minute unless you're a computer. But if you're a computer, you say, well, this is way too slow. I need to go way faster than that. An example of this is WSJT modes do a heck of a lot better than CW. And inside of that 2500 kilohertz, I didn't compute how many bits, but it's a lot better than you could do with CW. So it's just a concrete example of that. You can put a lot more information in a channel than you could do just with CW. So we already mentioned that we need more degrees of freedom, and that synchronization is important for coherent modulation, which we're going to use. We also have to imply that the channel problems are fixed. If there's multipath, fading, or non-flat behavior, all those things have to be fixed for this to work. The channel capacity is only valid in an AWGN channel that has no multipath. If those things are present, then the relationship doesn't hold. So just some, I should have mentioned this. This is a picture of this on-off keying. We all know what this looks like. It's just Morse code. So if you have a pulse, you can figure out what the two-sided bandwidth is based on the duration of the pulse. So this 1 over tau is the one-sided bandwidth. So the two-sided bandwidth is the duration of the pulse, 1 over that. So there's some confusion what Nyquist means. Some people say you need 2 times the maximum rate. We really need 1 times the two-sided bandwidth. So the rate is the 2 times this rate would be twice this. But if you just say the two-sided bandwidth, which we'll explain more what this is in a minute, then it's Nyquist equals two-sided bandwidth. Okay, back to some modems. The 2 big points that we've talked about, which maybe aren't that clear, you can put a lot of information through a channel, a lot more than CW, but it takes a lot of complexity. The second is a very severe channel impairment, way worse than we could do by ear, can be dealt with, are routinely handled in all sorts of modems. We're not going to talk too much about multipath and equalization here at all, but that is directly related to this topic. But in all these cases, when you use degrees of freedom, you use coherent modulation, and you want to do some kind of channel impairment correction, equalization, you gotta do synchronization. This is required, it's implied, but it's seldom stated. So we just back to the Shannon limit. This is just reiterating things we just said. We want to use modulation, degrees of freedom, but we need to do synchronization if we want to do impairment compensation. Coding is what people are more familiar with. It never says it, but it always assumes synchronization has been established. When I started learning about modems, I kept wondering about this. I said, well, how does that work if you don't even know if there's a signal? And they would always brush it aside. But it turns out it's the most important thing before you can do coding. So now let's talk about coherent modulation. So synchronization doesn't make a lot of sense if you don't know what coherent modulation, demodulation. But broadly, what it means is when you know what the signal frequency is and it's perfectly aligned phase in your detector, so your transmitter and receiver have the exact same phase and frequency relationship, where frequency is the rate of change of phase, then it's considered coherent. This requires tracking all of the parameters of the transmitter and the channel as they change. So not only correcting for them, but tracking for them as they drift. So we'd like to examine this problem, but there's a lot of background stuff that maybe some of you guys don't know. So I'd like to just touch on what complex baseband is and complex signals in general. To do that, I find the most useful thing to understand is modulation domain. This is not something that we normally deal with, but it's really valuable. So we all know what the time and frequency domain are, especially if you use one of these fancy little scopes. Time domain is just on and off. Frequency domain is a spectrum. So you can put those together and you get frequency by time. So this is well understood in the amateur radio community. But what's missing is phase. So the spectrum has phase and the time domain has phase, but we can't see that here. And we don't really think about phase. But phase is another degree of freedom. So modulation domain expresses the phase as part of the relationship that we're looking at. Modulation domain is where all the information is. The carrier doesn't really have any information other than whether it's present or not. Modulation domain, which is how the carrier changes, contains the information. So here we have a time domain signal, we have a frequency domain signal, here's some data, but this is the thing we're after. This signal here actually consists of all these states. And what these states are the I and Q values. And I'm sure most of us have some idea what an I and Q value is, the in-phase and quadrature components of a signal. However, that's an important concept, and we're going to look at it in a little more detail. But if we just consider the in-phase and the quadrature component as axes, or a basis function, we can say, oh, well, there's a combination of values that gives us a state. So here's 4 states. This is QPSK, or it could also be offset, it's just QPSK, offset QPSK. So you could either put it on the axis or off the axis. So there's 4 different modulation states. So here we're on and off, that's one state. We can be at some frequency, but here what we're saying is we're at a phase state and an amplitude state put together. So these exist simultaneously. And each one of these blue dots is a point in time. So here, time is on the vertical axis, time is on the horizontal axis here, time is into the page here. So at each sample point, we draw a dot. So time is into the page, and then this is amplitude, in-phase quadrature, and the angle is the phase. So the modulation domain is typically complex I and Q envelope. It doesn't have to be I and Q, but this is something that's most commonly used. It can be frequency, it could be polarization, it could be a lot of different parameters provided that they're orthogonal, which just means you can make an axis, basically. That's a simplification, but it's essentially that. The carrier frequency is a stationary parameter. It doesn't have any information. If you just have a carrier, an unmodulated carrier that's on, you can't tell anything other than it's on. So over time, if it's always on, it doesn't tell you anything. But you do need to determine its frequency. The I and Q are the orthogonal basis, just like X and Y. X and Y, if we make little vectors, are orthogonal vectors. Their dot product is 0. so that we can form a set of coordinates. So in-phase and quadrature components are just that. These I and Q, when you modulate it on a carrier, rotate around at the carrier frequency, but their angle, their relationship in terms of being orthogonal is always preserved. So you're not distorting, you're not, in an ideal system anyway, you're not taking some of the I and sticking it in the Q channel. Although that does happen in a real radio, and it has to be corrected for. So a special thing, let's see, do I want to do it that way? Maybe I want to do it this way. So here's what I just said in words in the picture. So here's an X and Y axis, which everyone knows about, I think. And you have a vector, 1x, 0y, 0y, 1x. If you take the dot product of those, which just tells us what is the projection of this onto that, it's 0, because these are orthogonal. We can do the same exact operation with functions. This is actually exactly the same thing. We choose functions that are orthogonal. We take a cosine and a complex sine, I and Q, in phase and quadrature. Those functions, which are a function of omega t plus phase, are also orthogonal. If we compute the dot product of these, and you can look at this link to get the complex dot product, you'll see that that is also 0. So although these are not numbers, they're functions. So, and they change in time, but their orthogonality is always preserved. So that just means that if we multiply these by a value, an amplitude and sine, and amplitude and cosine, that we can create a plot of things just like we did with X and Y, and that's what these are. I and Q. And then for a digital system, we pick a specific state. So we can do the same thing. Here is that repeated, a function of the same frequency. Both this one and this one have the same 2 pi f. But we can also choose real functions of 2 different frequencies. And this is what FSK is. And we can choose these at special frequencies such that their dot product is 0. It's harder to compute this in a compact form, but if you draw them out, you can see that their 0 crossings occur simultaneously. So we can do it with functions of the same frequency, functions of different frequency. These are all different ways to create a modulation signal with additional degrees of freedom. So WSJT modes are in this. It's doing multiple FSKs that are, I'm not sure if they're quadrature or orthogonal, but they probably are. Someone has to check me on that. So now we go back to here. We say, okay, well, how do we generate an equation for these things? So we all know what a real signal is. You just take a cosine, you change the phase, change the frequency, change the amplitude. A sine is just a 90-degree relationship to that. And if we look at a real signal in a spectrum analyzer, what we see is this blue side, because the spectrum analyzer just shows this positive frequency, but it always has a negative frequency. It's symmetric about 0, and it's anti-phase symmetric. So this guy's phase is down and up. So the spectrum analyzer shows us the real, but this imaginary part, this negative frequency always exists. So an analytic signal is a special kind of signal that has only one side. So we can create this without that. That's this bottom thing here. And we do that by forming this kind of signal. We make cosine and sine that are in quadrature at the same frequency. And what this does is it gets rid of one of this side. Because this is symmetric about 0, this is anti-symmetric. When you sum them together, it cancels this side. So it's only on one side. Since it's only on one side, we can do something really cool. And that is, we can make a signal that has some bandwidth. These are all just single sinusoids, have a different shape on either side of 0. So a real signal is symmetric. A complex signal or an analytic signal does not have to be symmetric. And we use this all the time, and it's single sideband. This is a single sideband signal. But instead of having this little blip over here at negative, we just use one part. So single sideband looks exactly this. If you look up single sideband, these equations will look really similar. So then we can say, all right, if I can make any shape, and it doesn't have to be symmetric, then I can really make any signal at all, anything, as long as I have the right parameters. So this guy is probably fairly simple. It has a frequency, it varies in time, and it has this cosine and sine. But now you can control the amplitude of each one of those components. That's this amplitude I and amplitude Q, which we know about. We can control the phase, the frequency of these. This is omega, but we can vary it in time. This tau variable is, instead of time being as these sine and cosine traces out, it's a second time where this parameter changes. And we could also do that to this, but I'm not in there. So this could be tau and t. And then we can add phase modulation that's different in I and Q. And we can also add a constant that's different, and that can change in time. So with these parameters, we can make literally any periodic signal that's possible. And even, well, it doesn't even have to be periodic for that matter. It can be a pulse. So every single signal that's possible to make can be represented with a series of these things. Okay, I did that. So just to review complex baseband, we can have any signal be asymmetric. We can have nothing on the negative spectrum. We can have something on both. So that when we upconvert that relationship is preserved. And that's what a single sideband is. But when you upconvert this by a real signal, the negative frequency does come back, because when you multiply this by a two-sided signal, these two arrows, you get this back. But you can't observe this in a radio system. It's present so that this is now symmetric around 0. But the part that we observe is this piece. This is always present, but we don't observe it. But when you downconvert it, this comes back. So with that format that we said, we can make all of these things: on-off keying, FSK, single sideband, MPSK, which is this phase shift keying at different levels, minimum shift keying and Gaussian minimum shift keying, which are just spectrum shaping that use special filters, linear frequency modulation, which is used in radar and ranging, quadrature amplitude modulation, which is what this thing is, and then OFDM, which is a huge, complicated beast. I'll just mention it here, so if you guys never heard of it, look it up. It's cool. Was there a question? Nope. Okay. You guys getting tired? Nope. Okay, good. Okay, so we talked about that there's states in the modulation domain. Here's this chart again. Remember, time is into the page, so each one of these points is a point in time. We have I and Q, which gives us a state. So each one of these dots is an amplitude and a phase. So here is a pulse. If we had amplitude shift keying, we just turn this thing on. So on is some magnitude. And here's phase shift keying, where we just did a 180-degree phase shift. But here we can shift whatever phase we want. So we picked 4 different phases. So we're controlling the amplitude like CW, and we're also controlling the phase, which we don't normally do. I'm gonna take a drink. Okay, so each one of these states is a complex number, and that complex number is referred to as a symbol. So what we want to do is have some mapping between these symbols and a number of bits. Here's examples of many, many more numbers of states. 512 QAM is 512 of these little guys. So you can put, what's that, 9 bits of information on a single channel. The latest Wi-Fi standards are up to 1024 QAM, which is just super crazy. So each one of these points, now we have four states. So if we have 4 states, we have 2 bits. You can also do this with frequency. It's much more difficult to visualize, because here's the IQ spectrum. Frequency modulation just moves around in a funny shape. But because we can draw a different set of axes, you can visualize the states as combinations of these frequencies. And here's a good explanation of that. If you guys don't know about Stack Exchange, it's pretty cool. They have that and the DSP links that I have. So a regular FSK system, the tone is on or off, 1 or 0. But in OFDM, it doesn't have to be true. Every frequency can have modulation on top of that. So this is really complex and it's awesome. All the Wi-Fi stuff is enabled by OFDM. Digital broadcast TV, Bluetooth, everything is all OFDM. This is spectacularly complex though. So here's our states. This is 16 QAM. And we have 16 states. We need 4 bits. So we pick a bit pattern that corresponds to each one of these states. And typically they're gray coded so that you have only 1 bit error between them. That's what good mapping is. It means that if you change a symbol, you have a symbol error that you only get 1 bit error. The other thing you can do is when you have a larger and larger constellation, these outer states are a much larger amplitude than the inner states, which means more power. So that's when you see this kind of truncation. What they did here is they said, well, we need too much power here, so we'll just take away some of these. And the other thing they do is they say these symbols will choose to be less frequent bit patterns. So if you just have pure random data, that would never occur, but in text or in some image data, there are less frequent combinations that can be mapped out here. Instead of just a simple gray code, they would map these according to symbol probability so that your average power is lower. So how do we increase channel capacity? We did already talk about this, but as a review, we've created this modulation domain where we have degrees of freedom, I or Q, or multiple frequencies. The bandwidth is still proportional to the rate of change, so that the Nyquist criterion is satisfied. However, with more degrees of freedom, we have states that correspond to more than 1 bit. So for a given symbol rate, more bits are sent. So in CW, we have 1 bit per symbol on or off. In 128 QAM, you have 7 bits per symbol. So if they were transmitted at the same rate of change, we can get 7 times more information in this 128 QAM. But this is coherent, necessarily coherent, so we have to do synchronization. So this is what we just said. There's some cost. Of course, nothing is free. We're putting more information in the same bandwidth. What are we giving up? What we're giving up is these states are closer and closer together so that the error rate goes up for the same amount of energy. And you'll see that in this bit error rate curve. So for a Gaussian channel, which is just a flat noise that we talked about, which is why we talked about it, because you'll see this, and I wanted you to know what it meant. We know that here's our energy per bit to noise in 1 Hertz ratio, proportional to SNR, and here's our bit error rate, which is the number of errors per bit transmitted. So BPSK and QPSK, they're exactly the same, because BPSK and QPSK, BPSK is just 2 of these. QPSK is orthogonal to BPSK, so the error rate's the same, the performance is the same. But if we go to 8 phase shift keying or 16 QAM, you see that for the same amount of energy per bit versus noise, or SNR, our bit error rate is quite a bit worse. Here it's 4 orders of magnitude worse. Ooh, I'm getting weird feedback somehow. That's what we pay to get that capacity. So this is where our channel coding was used. Here we see, okay, if I use QPSK, I have much lower error rate than if I use 8PSK. But if I put coding on 8PSK, now I can push this all the way back down. So the choice of modulation is the rate and the available bandwidth, and then the error rate comes from the coding. That's how those things relate together. We choose the modulation type based on what our channel conditions are and how much bandwidth we have, and then we choose our coding depending on the desired error rate. Okay. So I wonder if that's me. I have some strange feedback. If we just assume that we're synchronized, which means that these constellations are perfectly aligned and they don't move in time, how do we detect these different modulations? I'm going to talk about just hard decision. There's this whole thing called soft decision, but it's much more advanced. What we do is we use what's called a slicer. So in the modulation domain, you have these states, and you put a decision point where these dashed lines are. So if you're in this square, you're this symbol. If you're in this square, you're this symbol, 0, 1, etc. So it's just saying, okay, I'm either here, or I'm here, or I'm here, or I'm here. And this is an important to understand in terms of why synchronization is needed. So once you have these bit slicers in place and your clock and frequency and phase are all known, you can just say, oh, if I'm in this square, this is the symbol I want, and I just look up this region gets me this value. It's simplified, but this is essentially what's happening. In frequency division, where we're using FSKs, we do the same thing. We say, if this tone is on, I have this symbol. If this tone is on, I have this symbol. And so we're slicing in frequency instead of amplitude in I and Q. This circle here is what happens if you have this signal and you're not synchronized. So in this signal, no synchronization has not been established. So if you have this decision boundary, here's the decision boundary, but this is moving around. So you can't tell what symbol to pick. You don't know. So this is why synchronization is crucial. To do this decision boundary detection, determine what the correct symbol is, you can't have a spectrum that looks like this. So this is probably a phase offset, so the constellation is rotating, but it could also be a slowly changing phase error, because those two are not distinguishable. In the frequency domain, it looks a little different, because phase isn't important. You can do frequency, you can do FSK without knowing phase. There's some trade-offs, and we saw those earlier. Let's see if I can find it. Backwards, here we go. If I have FSK versus coherent modulation, my error rate is significantly worse. And that's what we pay. We say, okay, we're not going to phase synchronize, but this error rate's much higher. And we still have to know the frequency, though. Okay. Where was I? Here. Okay, so more about synchronization, especially relative to all these other things. Whenever you see a bit error rate curve, a link budget, channel capacity, computation, they're all reported assuming that synchronization has already been done. If they don't say it, it's just understood that it's done. They just kind of gloss over this, and no one ever says, oh, you have to do this, or how to do it, or how important it is. They just say, oh, well, somebody already did that. It's also frequently after channel equalization and gain adjust has been done. That's also not stated, and it's also necessary. So what this means is that these guys showing these curves assume that all the transmitter receiver deficiencies and the channel effects have been removed. Then I can show you these curves. So we need to fix all these things: amplitude variation, frequency offset, phase offset, clock rate, and sample position, and channel impairments. This is what synchronization is all about. Fixing all the things so that these things will work. To me, this is what's cool. Like, a lot of people really like coding, but I think fixing these things is the most interesting thing about modems. Synchronization. So if we just temporarily ignore what the channel does, primarily multipath is the worst one, because this by itself is a whole giant amount of stuff. We'll just forget about equalization. We'll just think about synchronization. And then what do we need to fix? We have to figure out what the receiver gain should be. And then we have to know, is there a signal? And if there is a signal, where does it start? The frame, the packet, and the message. We didn't talk about these structures, but it's good to know about what they are. And anybody that's done packet probably knows a little bit about this. But you need to know where they start as part of synchronization. Then you also have to know precisely what the frequency is. If you don't have the frequency right, the phase ramps. Or if you don't have the frequency right, when you do your FSK slicer, these will be in the wrong place. So it's really important. Whoops. There we go here. It's really important to know this precisely. And if it's coherent, which most of these modulations that we looked at are, we need to know the phase because the slicer can't make a decision if the phase isn't properly aligned. Okay, and then the last one is clock recovery. Once you do all these things, you have to know where the symbol boundaries are, because remember these points are, time is into the page. If you pick the wrong time, what'll happen is these points will move around and it'll cross the symbol boundaries. And that's more easily seen in an eye diagram, which we'll show. So these are the primary things you have to do for synchronization. Ignoring channel equalization, you have to make sure you have the right gain. You have to know when the signal occurs and when does it start. You have to adjust its frequency. You have to adjust its phase. And you have to find out where the correct symbol boundaries are. And then all those things may move in time, so you have to track them. Not only adjust, but track them. So unfortunately, every one of those things could occupy many, many hours of me talking, and you'd all get bored. So I'm just going to do it really fast, especially since it's almost 9 o'clock. And I'm just going to do detection, frequency adjust, phase adjust, and clock recovery. These are the main things. And if you know about these and you have some of these links in this presentation, you could actually learn much more about it. First thing you got to do is there a pulse. Here's a curve with noise. There is a pulse in here. The thing is, where is it? How do you know what's the pulse and what's noise? Like, is this interference or is that my signal? I don't know. There is a pulse there, but the thing is, where is it? In packet systems, which is mostly all machine-to-machine communications or like voice over IP or fiber or anything, everything is packetized. There's a whole bunch of reasons for that, which are outside the scope of this, even outside of coding. But everything in the modem dealing with equalization, which we're not going to talk about, and coding needs to know exactly precisely where the start of the message is. If you're off by 1 bit, everything fails. If you're off by a fraction of a clock period, everything can fail. So if you don't synchronize, starting with where's the start of the thing, whether it's the preamble or the actual data packet or the any portion of the correction, it'll fail. So that's crucially important to be able to detect the beginning. The obvious way is just to set a threshold. However, when you're in low signal noise ratio conditions, which is almost always in a properly designed system, not in amateur radio because we like to have loud signals, but in a properly designed system, you want to use the minimum power you possibly can use to, say, conserve battery life or save money on electrical power. So it's always a low SNR condition. The setting a fixed threshold is extremely difficult. Basically, it's impossible. When it's properly implemented, these modulation schemes look exactly like noise, which make it look even harder. Because the maximum information you can put in a channel comes close to the statistics of noise. If you dug into the Shannon channel capacity proof, you could begin to suss this out. Is that as entropy is increased, the information matrix, which is how you mathematically statistically describe information, converges on that noise. So it should look like noise. It should look as random as possible to use the whole channel, which just means it's even harder to do this. And then if there's interference, which might be larger than the signal, there's no way to distinguish the start of the signal. And then, of course, the signal strength varies orders of magnitude, even within a packet, especially when there's strong multipath. A typical way to do this is with an auto and cross-correlation relationship of a preamble, which is a special portion of the packet with a modulation that's crafted that doesn't contain bits. It's just used to do synchronization. I started making a bunch of slides to go through this, and I realized there's just too much stuff. So I'm really just going to truncate this here to say that there are these methods that are very important to be able to determine where the start of the signal is. And they're much more complex than I originally thought when I started learning about them. And a great place to look is if you look up the anything standards. They all use a very similar cross-correlation method in the preamble. Frequency adjust is a little more tractable to do some explanation. If we took that 16 QAM and the frequency is wrong, what would happen is it would spin. So here it's not too bad because it's not spinning all the way around. It's just spinning a little bit. But when this spins, you can see that the symbol boundaries are not clear. You don't know, if you just made a fixed boundary, you couldn't decide what's right. It should look like these blue dots, but instead it's spinning around. And here, we don't even know what this modulation is. Could be PPSK, QPSK, MPSK. It's just spinning around. You can't tell anything because the frequency is an error. And this may only be a few percent, or not even that. The frequency precision of Wi-Fi has to be, I think, less than 50 ppm as a total budget. So that's really, really close. So it's super important to adjust the frequency. If nothing else, we want to stop this constellation from moving in our IQ phase space so that the dots are distinguishable. So after we adjust the frequency, it's still not phase aligned. So these blue dots are what we want it to be. So the gain is off, which we would do during detection and thresholding. So that hasn't been done. And then, although the frequency now is adjusted correctly so that the phase is fixed, the phase is still wrong. So if I made a symbol boundary, I'd still pick the wrong thing, especially with these more noisy outliers. So I adjusted the frequency, I stopped the spin, so now I can tell what the heck is going on, but I still need to adjust phase. So frequency is a rate of change of phase. So when frequency is off, the phase changes, so it spins. In the IQ, imagine time is into the page, but each one of these samples, like if I pick this sample, the next time I see it, it's going to be somewhere else because it's moving in a circle. Although you can do that with a phase lock loop, you can only do it with a very small frequency error because you'll get a fast ramp if the frequency's off a lot. Also, in a packet-based system, you don't have very much time to do this. So typically a phase lock loop for a large offset will take longer to settle than a frequency lock loop, which is one way to fix it. Every transmitter and receiver, no matter how good it is, has small frequency errors. And typically, even if they're as good as you could possibly get, they're still too big. Like if we have an oscillator that's 10 ppm and we do FT8, the FT8 algorithm still has to adjust the frequency, even inside that 10 ppm. I don't know exactly what his frequency tolerance is, but it's very small, to make sure the phase does not change inside of the symbol period or inside of the packet frame. In Wi-Fi, the packet is only a few microseconds, but you have to hold the phase constant within the symbol boundaries over that whole entire packet. So from the beginning of the packet to end, if it's 1,000 bits and we're at 20 megabits per second, this has to stay fixed during the whole packet. So having the frequency adjusted to prevent ramping phase is really critical. Oops, where did I go here? Okay, so this is a bit of an eye diagram, but if you've ever seen a phase lock loop, I'm going to take a drink of water. Frequency lock loops have been around just as long. They're not as common in literature, but it's very similar. Here, if we just look at how this is constructed, I have some device that computes frequency error. The state machine is just a function of how this is implemented in a packet system. I adjust the frequency and I hold. And then I have a loop filter, which has the gain and frequency response characteristics. And then I go into a voltage controlled oscillator equivalent. Here this is digital, so this is a numerically controlled oscillator that adjusts the frequency. So although a frequency lock loop sounds confusing, it's basically a phase lock loop that has a frequency detector instead of a phase detector. In this case, I have a specially constructed preamble that I know that when I have the right frequency, the rate of change of those samples in the IQ domain will be separated by a fixed amount. And then I can look at the angle. This is probably confusing, but the point that I want to get across is that a frequency lock loop is very similar to a phase lock loop, except it adjusts frequency instead of phase. So the next thing we want to do is align the phase. So we showed this signal that wasn't aligned, we want it to be the blue dots. And if we adjust the phase, and it looks like this. So we're just taking this and we're twisting it. Again, this may move in time, especially if the frequency is adjusted initially and then drifts. The phase lock loop has to track it all out. So it could be moving in time. Here's another example of a noisier one that's on an angle. This is a cool example. If we had BPSK that was perfectly phase aligned but 90 degrees out of phase, since we're only bit slicing in these regions, we'd actually get no data at all, even though it's obvious that we have a very high signal noise ratio. So it's really important that this is rotated such that if we put our bit slicer here and we say, is it here or there, that we can see something, versus if we put our bit slicer here, we just get nothing. That's the phase align. These are all coherent modulations, which basically means the phase matters. This is a 16 QAM, and this is a BPSK. So the other thing you can say is if I have QPSK, it's just two BPSKs that are in quadrature. So if I stick this on top of here, I can double the information rate with the same amount of power. Here's the simplified phase lock loop that we're probably mostly familiar with. You have a signal, you have a phase detector. It produces an error signal that's filtered with a loop filter, and it controls an oscillator that adjusts the frequency. So in this situation, what happens is we lock this oscillator to this signal, but it's going to lock it to the average phase. If we have very slow modulation, this will just track it right out. If we have fast modulation, either the loop won't lock at all or it'll lock to some funny phase. So the point here is if you just use a regular phase lock loop and you have modulation, it probably won't work because the phase is jumping. So when you have a phase discontinuity here, this guy's impulse response is excited every time, and you'll get something other than what you want. We won't get an aligned signal. We'll just get something that's not really useful. So there's something else we have to do when we have modulation. You got to remove the modulation in order to align the constellation. There's a lot of ways to do this. The one that's probably most interesting and a good place to start is this thing called a Costas loop. It's really clever. It's used everywhere. And a Costas loop, let's ignore this bottom part. We could look at this upper part, and it looks an awful lot like a phase lock loop because it is a phase lock loop. However, we added this lower branch, and what this does is we put a 90-degree phase shift in, and then we multiply this signal times this upper signal. So if the modulation is an M term, what we get is M squared. So if we have BPSK, when we square a -1, we get a 1. So no matter what state we're in, 1 or -1, this signal stays the same. So since this signal stays the same, no matter what the modulation is, this loop will align the data correctly and output the aligned data. So the regular phase lock loop will not track the state, and it'll give us something wrong. But this will, because it's called a decision-directed loop, it uses the data itself to decide what the polarity of the loop filter input is. We get out aligned data. Costas loop is another topic. It has a whole lot of stuff. Like what's the statistically best version of this, depending on the signal and noise ratio? How do you construct this for different kinds of modulations? But simply by knowing that Costas loop is a thing and having this idea that what you're doing is you're multiplying this constellation in a power to take away the change, that is enough that you could dig into it further. Wikipedia has some interesting things before and after the loop is closed. So here you can see exactly what I was writing. You say here you have a modulation signal and a carrier term that's multiplied by this local oscillator. But the takeaway is these guys, when you do this power relationship, that modulation term disappears in the error signal. So even when it's not locked, that M term goes away because, this is specific to BPSK, because if you have a -1 and a 1, when you square that, because it's this guy's M, they're multiplied together, it goes away, that this will now have a negative feedback that will lock. So after it's locked, the frequency offset goes away and behaves exactly like a regular phase-lock loop. This is a cool trick, and there's a lot of versions of this for different modulations, for different schemes, for different signal-noise ratio that you can look up now that you know it exists and have a general idea of how it works. The last thing I want to talk about is clock recovery. If you have synchronous data, which just means it's some means exists to synchronize it already, we have a clock and we have data. So here, if we use the transmitter clock, we just say, oh, I know when to sample. I sample right here. But if we just have data and we don't have this, and we have some other clock that's not aligned, sometimes it'll be right and sometimes it'll be wrong. So these clocks have to be at the same frequency, but we don't necessarily know what frequency the transmit clock is. So we've taken out the frequency error, we've aligned the modulation phase, but the sample time could still be wrong. So here is a BPSK signal. We don't know what the symbol rate is. In fact, it's different between these two sections, and it may be drifting. So if we just use the fixed clock and we took a guess, most of it would be wrong. So you have to have a way of figuring out when we should sample. A good way to examine how these things work and what is going on is an eye diagram. I don't know if you guys have been exposed to eye diagrams. Here's a link that has a good explanation. Basically, it's just this. You have different data states. So here's a positive transition at time 0. Here's a positive transition at time 1. Negative transition time 0. Negative transition time 1. If you take all these time slices and you pile them on top of each other, which is what would happen if you took an oscilloscope probe and just put it on a data stream, these will overlap. Assuming that they're synchronized, the clock rate is known, there'll be this region that's called the eye. It's open because the transitions are aligned and the states when it's not changing are aligned. So here is a 4-state system. And this part, we know what the clock is. So all the times that where we want to sample are aligned. So this eye is open. Here's the little eye. This is the period where the signal is changing, so they're crossing each other. So if we didn't recover that clock, we just get this. So if we said, okay, what's the symbol value here? There's no way we could tell. So it's important that the clock is precisely aligned with the transitions of the data with this. But we don't have this. We have to get it from the data somehow. There's bunches of ways to do this. We know the frequency is adjusted, so the phase is not ramping. The phase adjusted, so the constellation is aligned. The slicer can decide, but it has to know in time when to slice. Remember, with these constellations, time is in the page. So all these things have recovered clock. If the clock wasn't recovered, it would be smeared the same way that this is smeared. So the thing is, how do you know when to sample? You could look at the data and you could guess with a pen. Like here, you could sit there and say, oh, I think it's this one, and this one, and this one, and this one. You know, if you were a trained artificial intelligence neural network, which we all are, I guess. But there has to be an easier way that's automatic. If it's low signal noise ratio, you couldn't do that. Like even this, because it's 4-state modulation, there's no way you can guess. So there's a lot of ways to do that, like all these other things. These are the main ones that if you want to look up, you could see. Probably the two most commonly used are at least in the explanation or pedagogical sense, which I don't really like that word, but it's a good word. Early, late, and Gardner algorithm. A delay lock loop looks almost exactly like a Costas loop, except it uses time delay instead of frequency, and it's implemented very similar for clock recovery. And polyphase interpolation is probably one of my favorite. Using a multi-phase filter and a polynomial interpolation scheme, you can resample data. So these algorithms have limited ability to recover clock that's very far off, more than say 1% is very far off. And especially if the rate is changing, they can often fail, but polyphase is better for it. So here's just a very, very brief taste of clock recovery. So the early late assumes a lot of stuff that we didn't talk about. A match filter, an integrator, all these things. But if we had square wave pulses and we had a match filter, which you don't know what it is, but you should look it up because it's a whole other topic, and you went into an integrator, as the pulses move across each other, you get a triangle. So if you sample at the right point, you'll have an early sample, a desired sample, and a late sample, and their amplitudes will be equal. But if you're early, what happens is the late is bigger than this sample. Or if you're late, the late is smaller than that sample. So by using the amplitude of these three samples relative to on the output of your integrated pulse, you can figure out what the right one is. So one thing that's important to understand about this is if your clock rate is, say, 1 sample per second, you actually need 3 samples per second to figure out what the right time period is. That's not something that is easy to get from literature. If you just crack open a book on this, it's sometimes confusing to realize you have to have multiple samples at a higher rate than your data clock to make this work. The Mueller one is very similar. It's just a different way of computing this using a mesh filter. But it's the same idea, though. This, instead of having these closely aligned samples, they're farther apart. So you have this plus-minus relationship. But this and this are very similar. So you have more samples than your clock rate, and you compare the amplitude of them to create an error function that says, am I too soon, am I too late? And both these links talk about these algorithms a lot better than the 5 seconds I'm spending on here. The Gardner algorithm does exactly what these do, but it only needs 2 samples. So this is very popular in lean implementations because it's computationally efficient. And then polyphase interpolation is used in a lot of things where Doppler is a problem, like satellite modems and mobile communication schemes where the clock rate has Doppler.
Jessica, can you hear me?
Yes.
On the some examples page where we were talking about early and late.
Okay.
Yeah, what is a UI?
Where are we looking at UI?
On the right-hand side, we're talking about time or...
Oh, unit interval.
Thank you.
Yeah. So the thing that really messed me up on these, and I just want to reiterate that, is that, let's say, like I said, if your clock rate is 1 clock per second, it's really important to understand that this is 3 clocks per second. Like, no one says that anywhere when you read this, and you're like, how does this work? That's important. These triangles come from a match filter and an integrator, which we didn't talk about, but that is a crucial concept to understand how these waveforms are created. But if you know about the fact that you have more samples per unit interval than your data, then this will make a lot more sense. Okay, so very last slide. Oh my gosh, 9:10. I mentioned equalization a bunch of times. This is an advanced topic, but it definitely needs to be mentioned. What we assume in the channel capacity is that the channel is flat in frequency. The noise is flat and the frequency response is flat, and it's not changing. But that is completely bogus. No channel for any modern wireless communication scheme looks like that. They all look horrendous. Primarily, it's multipath, especially in short-range and indoor environments. Multipath can be extremely severe. Each one of these signals is an echo, and echoes act as delay taps. If you know at all what a finite impulse response filter is, delay taps make a filter. So that filter means that the frequency response is not flat. It also, if the multipath is long, can introduce intersymbol interference. And what that means is, if we have this symbol, if an echo from this guy is delayed long enough, it'll show up in this interval. So somehow we have to know that that happened and fix it. Now, some modulation schemes introduce intersymbol interference on purpose to increase channel capacity. This gets really complex. But knowing that multipath is a very severe problem and it must be dealt with will save you a lot of headaches if you try to do something where multipath matters. So anything with more than a very small bandwidth. So more than let's say a few hundred kilohertz, and the bandwidth that matters is a function of the path length. So an indoor path length, you got to be in the tens of megahertz, where the path length is impacting the channel frequency response. But if you're outdoor, where the echoes might be from a mile or 10 miles away, then much narrower bandwidths can have this. Where you would experience this, at least us older people, is that in the analog FM TV days, or analog AM TV days, when you had multipath bounce off a building, it would give you shadowing. That's exactly what multipath is. It's a really, really bad problem for data communications. I guess I'm harping on this simply because it's frequently ignored by people that don't know about it, and they propose these crazy schemes that they think are going to work great, and they completely fail, and eventually they figure out why. This is multipath. At HF, we don't really ever experience it because the wavelengths are very long, but you could, if you tried to implement a digital communication scheme, have an issue with this. And some of the ARQ methods that are used, especially in marine transmission, do have to deal with that. At microwave frequencies, because the wavelengths are short and the bandwidths are wide, it is absolutely necessary to fix it. All wireless standards include equalization of some sort or a way to deal with multipath.
What are the bandwidths at Wi-Fi?
Like 802.11 B has 6 or 8 different modulations, but more or less everything is about 20 megahertz because it's OFDM. Okay. Now, the really cool thing about OFDM is OFDM allows a frequency-dependent fade to be treated as a flat fade. And flat fade means that the frequency response is flat. And they do that by individually weighting the carriers. That is the main reason why OFDM is used. It's an extremely powerful way to fix this problem. And with that is my last little bit of information that I was hoping to communicate. I didn't even write it here, but OFDM makes
Thank you.
a flat fade. So there we go. That was a huge amount of stuff, pretty fast. Like, I'm not giving any of these topics justice, but it's enough that you could dig into it. I'm hoping that it's enough that if you read something, it'll make a little more sense. Look at all the links. Every one of those images that has a link usually has an explanation. That's a lot better than what I gave you. And it would be fun to spin some talks out of this if you guys had some interest. Thank you very much.